the next one will be. So we plan to have people talk about density functional theory and electronic structure method. And some of them also will be on topological insulators related to condensed matter. So it will mainly be things related to condensed matter. And of course, electronic structure is related to condensed matter. So it will be things mainly related to condensed matter. At the same time, we'll have colloquial sessions. The colloquial will be one every month, and it will be in topics in high energy physics, high energy cosmology, and astroparticle physics. It will be topics in geophysics, and it will be in topics of condensed matter. So once a month, we'll have a colloquium, in addition to these seminars that we'll be having. We will advertise the colloquial way in advance so that you can join us by Zoom. So today, we are having a condensed matter physics seminar, and the seminar is given by Professor Krzysztof Szalewicz. He's a professor of physics at the University of Delaware, but he's an adjunct, he has a joint position in the chemistry and biochemistry department also. So I'll tell you a little bit about Krzysztof, and then he will start. So Krzysztof got his PhD in 1984, a long time ago. And then he was in Gainesville in 1985 as a research scientist. And then in 1988, he moved to University of Delaware, where he has been till date. I met him in 1998. And over the years, he has taught me 2 courses and tried to teach me 1 thing. So 2 courses meaning he taught me math methods in 1998, the math methods 1 and math methods 2 at the graduate level. And then over the years, a couple of times he has tried to teach me skiing, which I have not been able to pick up. Okay, so Krzysztof Szalewicz, he will give us this talk. I'll just make an announcement before he starts. If you have any question, you can unmute yourself and ask the question. So Krzysztof allows us to do that. So just unmute yourself and ask the question. And then at the end, if you have time, you can also ask questions. In the chat, you can put your questions there also. Okay, so over to you, Krzysztof.
Okay, so I would like to start from thanking Omolulu for arranging this talk. I'm very pleased that I can share my research with so many people in such remote places from where I live. Just to be kind of closer to where Omololu is, I checked what is the temperature, and temperature at this time in Kigali is actually exactly the same as in Newark, Delaware. So at least we are at the same temperature. Okay. So I will start from thanking people who contributed to some parts of this talk, to results which I will be showing. Mike Metz, who used to be my student until quite recently, and Rahul Nihar. Actually, most of the work which I will show of our results are produced by Rahul. Javier Garcia is postdoc in my group, who is responsible for the new version of our programs. And I will briefly only talk about John Melkumov, who is another graduate student results. I don't have time to show his results, but I will mention them. So the research I'm talking about was supported over the years by Army Research Office and by National Science Foundation of United States. So I will start from telling very briefly why crystals are of interest and explain what is the meaning of the title of my talk, Crystal Structure Predictions. So what are crystal structure predictions as such, and then what are crystal structure predictions from first principles. So I will talk about force fields, which means forces between molecules, which can be calculated from first principle, which means using quantum mechanics, solving equations of quantum mechanics. We call such force fields ab initio force fields. Ab initio is basically the same meaning as first principles, or actually from first principles. It's just Latin ab initio, often used in this field. So I will then present our development, the one actually done by Mike, which I think changed this ab initio first predictions for crystals, automatic development of force fields. And then I will talk about new. So once we started to develop those force fields, you have to do predictions. You can collaborate with other groups, and as you know, collaborations are not always easy. So we eventually started to do ourselves predictions. Actually, we did it from the beginning, but now we did in such a way that we modified method, we introduced new methods in the crystal structure predictions, and this will be kind of main part of my talk. And then if time allows, I will tell you about what we are working on now, which are mainly larger monomers, use of fragmentation to build larger systems, and extension of this to include internal degrees of freedom of monomers. So crystals are beautiful, so that's one good reason to be interested in crystals. I found on the net this amethyst from Rwanda and a beautiful tanzanite, and there are more examples. And of course, crystals are useful. I just, again, picked from web some kind of random collection of books about crystals. And of course, there are many, many, many more of such books. So now you have crystal, and why do you care what is inside? So actually, this is very important. In particular, not only it is difficult to find out what will be the crystal structure of a given molecule. Actually, finding crystal structure is now very easy. You do X-ray analysis and you have it in no time. There are those beautiful computerized devices which I have seen in laboratories of my experimental collaborators, that you put crystal in and you have beautiful picture like those pictures on this page coming out in a couple of minutes. So that's one thing, is what is a crystal structure of a given molecule, but the problem is that there is no unique question. There are many, many crystal structures which are called polymorphic forms of crystals. Not all substances have polymorphic forms which can be crystallized, but many substances have large number of the order of 10 of polymorphic forms which can be found experimentally. The well-known examples are actually from kind of hard solid state physics. So this is this famous example of boron nitride, which crystallizes in hexagonal form, which is similar to graphene, in cubic boron nitride, which is similar to diamond, and then this Wurtzite structure. So I will not talk about such crystals which are will not talk about metallic crystals, salts and simple salts and stuff like this. I will talk about crystals of larger molecules like this one, which you see in the right corner, which is this molecule ritonavir, which is a pharmaceutical drug, very successful in HIV treatments. You might have heard about it recently. It was tried as a possible cure for COVID-19. Well, supposedly it doesn't work, but it kind of got back into light. So it is a famous example of why crystallography and crystal structure predictions are important. So after this drug was developed, it was put on market, and then after it being on market for some time, like 2 years, I believe, people found out that it doesn't work. And after investigation, they found out that in this industrial scale manufacturing of this drug, they produced a different polymorph, which had different bioavailability and had virtually no therapeutic effect. So the drug was withdrawn from the market for 2 years, and then they found out how to produce this right polymorphs on industrial scale. This is one of the most, ritonavir is considered to be one of the most successful drugs in the history of mankind, and it saved lives of probably hundreds of thousands of people. Another well-known example of this is rotigotine, which is a Parkinson and depression drug, which was again recalled for 2 years for the same reasons. And there are more of such examples. So in fact, in big pharmaceutical companies' labs, which develop new drugs, there are really thousands of people who are mainly trying to find various possible polymorphs of new drugs. It's a big industry, and pharmaceutical industry spends a lot of money on experimental identification of polymorphs. And well, I will talk, so that's why it is important to be able to do it on computer. And I will tell you what is the present status of replacing this expensive experimental research by computer simulations. So what are crystal structure predictions? So instead of doing all those experiments and spending billions of dollars, you could do it on computer, in principle. But in fact, it turns out not to be that simple. I will get back to it in more details, but in short, if you have chemical formula of some monomer, doesn't matter what it is, you have to find how the monomers interact, because crystal is really formed by intermolecular interactions. If you have this interaction potential, you can construct polymorphs, but the problem is that you construct a lot of polymorphs, like 500,000 of polymorphs. All are valid, which means that they have proper crystal symmetry group, everything is okay, but only one of them can be synthesized actually, or maybe a couple of them can be crystallized in lab. So which one? That's a big question. So there's the crystal of this molecule, and the question is how to find out of those hundreds of thousands of structures. And of course you say, oh, let's calculate energies and densities and properties. The problem is that when you calculate it, you get a graph like this. So on this graph, I'm showing here density of the crystal, and here lattice energy, so how strongly crystal is bound. And each point is a polymorphic form of a crystal, and the different colors are different symmetry groups. So you can see this is a real mess with many, many possible solutions. And I will tell you how we pick up the one which can be then found in the lab. So I first will talk about those force fields, the interactions between molecules which keep molecules together, and due to different dependence on orientation and distance are responsible for crystal structures. So since this is a widely varied audience, I would like to first say something very, very basic, and I apologize to all of them, to all of you for whom it will be very boring. So what is the definition of force field? So we are talking about quantum mechanics. So we want to solve Schrödinger equation for a molecular system. We have n electrons, n nuclei. So this is a very hard system. And if you want to include motion of all particles, actually it is solvable maybe for 8 particles right now, maybe 10. But if you instead clamp nuclei in space, assume that nuclei do not move, this turns out to be much easier to solve for several reasons, and we currently can get reasonable solutions for thousands of electrons, so for quite big systems. And this Born-Oppenheimer approximation, assuming clamped nuclei, is the base of much of chemistry. So everything which you have read in chemistry courses, orbitals, linear combinations of atomic orbitals, harmonic vibrational spectra, everything is based on Born-Oppenheimer approximation. So to put it into equation, you have a Hamiltonian, which is a function of electronic coordinates and a function of nuclear coordinates, where Q in our approach, you could just write here nuclear coordinates, but we like to think about each molecule represented by a set of Euler angles, distances from each other, and from center of mass, and of internal coordinates. So those Q characterize the nuclear framework. So you solve it for wave function, but when you solve it, this semicolon means that Q's are fixed. Only electrons are variable in this equation. So the energy, total energy of the system is different for each configuration of nuclei. And this total energy is the basis for this force field. Total energy is quantity which is sufficient to be considered, but it is convenient to consider interaction energy. So interaction energy, which also depends only on nuclear coordinates, is this total energy minus sum of internal energies of all molecules. And this interaction energy is a potential energy. We call it vertical interaction energy because we assume that those internal coordinates of each molecule are the same. They also are hidden in those Q's and are the same in Q's as here. That's why it's called vertical. So this is a potential energy. If you calculate minus gradient of it, you get force, and that's why it's called force field. Since calculation of gradient is kind of trivial, once you have force field, sometimes those names are used interchangeably, force field or PES or potential in the surface. Okay.
So,
yes.
So E tot is the same thing as V, right?
Say it again.
E tot, your E total is the same
yes.
thing as V.
Well, depending what V is.
Yeah, but V here is E tot, right?
Yes. So yes. Sorry. Thank you. Yes, I should have written here this V tot. E tot. Yeah. Yeah. Of course. Well, I meant here a general formula for F. F equals minus dot gradient of potential. Yeah, but it will be better. Yeah, okay. So force field and potential and surface, I will use it interchangeably. So how can you get this force field? So one way is to find some experimental data, do some molecular dynamic simulations of some liquids, for example, look at some crystals and fit parameters in some very simple functions to those experimental data. Those are called empirical potential energy surfaces or empirical force fields. So no quantum mechanics is really involved. Maybe the shape of this potential is somehow, related to quantum mechanics, but no ab initio calculations performed. The method is generally fast, but in crystal structure predictions, CSP, crystal structure predictions, it's really not reliable. There are better and better empirical force fields developed, but still they are not fully reliable. So then what you can do kind of on the other end of the spectrum, do periodic density functional calculation for electronic structure calculation for the whole crystal with periodic boundary conditions. So this is the same. It's a method which does not involve MD in crystal structure prediction, but it's very similar to ab initio MD, AIMD, the name which is now used for the method developed initially by Carr and Parinello, which is this periodic density functional applied in molecular dynamics. But I will not talk about AIMD today. So the advantage of this method is that there's no fitting of force field involved. Force fields are just generated on the fly. And by default, this method includes all electrons in a compute cell, so includes all many body effects, all non-additive interactions. But it's very expensive. It's too expensive to scan even thousands of crystals. And then the method which I will advertise today are those ab initio potential interfaces or ab initio force fields, which are fitted to quantum calculations and then can be used in crystal structure predictions in the same way as those empirical force fields, which is great because this technology is very well developed and you just use different force fields. So that's a significant advantage. So our group was one of the first to use such force fields in crystal structure predictions a long time ago. I will not talk about those old results, but what is new is that one of the problems of those ab initio force fields was that computer code development was really high for larger molecules, and it would be impossible to develop force fields for molecules such as some pharmaceutical drugs. But our group has developed, and Omololo worked on it, so-called symmetry-adapted perturbation theory. I will briefly tell what it is. It's not really relevant to understand what it is to understand our work on crystal structure predictions, but I will briefly tell you what it is. It's a method of calculating interaction energies, and then you can fit force field to those interaction energies. And then what is new, which we introduced recently, is that human cost of fittings were really huge. And we reduced them by using machine learning, and we have a program called AutoPES, Automatic Potential Energy Surface Development, which can do it now at basically zero human involvement. So to compare those three approaches, I compare it in the context of molecular dynamics because that's how they actually are usually compared, but it kind of carries to crystal structure predictions. So those empirical force fields, this is a huge field, and there are thousands of people doing molecular simulations, in particular for biomolecules, and they can do really impressive systems. They can do simulations for systems containing 1 million of atoms, and on this axis you have simulation time, and so this is in nanoseconds, so 1,000 nanoseconds is 1 millisecond, so they can do millisecond simulation for 1 million atoms. Very impressive. So it's fast, simple, universal, but accuracy is limited. On this axis, I have uncertainties of such potential analysis obtained used in this method. So really accuracy of those methods is like 10 kcal per mole, which is a lot because interaction energies are of the order of 10 kcal per mole. Then if you use ab initio force fields, the main advantage is that you are improving accuracy by 2 orders of magnitude. It's easy to obtain force fields which are accurate to 0.1 kcal per mole. Also, what is important that if you use this, it is really like using ab initio method directly in molecular dynamic simulations. Because if you have high fidelity fits, it's the same as if you use actually computed energies. We are trying to have our fits like couple of times more accurate, that have errors couple of times smaller than the errors of theoretical calculations. Those surfaces are almost as simple to use in MD as empirical potentials, can be made arbitrarily accurate, and in MD are also essentially as fast, maybe like factor of 10 slower, which is nothing, as empirical force fields. But they have problems. One big problem is development cost, which I already mentioned. We reduced very substantially, and I will talk about it. One problem which is not solved and will be never solved is dimensionality curves. If you make your molecule completely flexible, so which means all atoms can move, the dimensionality of system becomes huge, and you just cannot fit such huge dimensional surface. However, part of our work and work of other people shows that with proper approximations in number of dimensions, you can actually work out very well around, kind of find ways around this problem. I will say about it a little bit soon. And of course, they are system specific right now, but again, there are ways of making it more universal. And then finally, the Scar-Parinello type methods have several advantages, are universal, are simple to use, include many mode effects. That's very important, as I already said this. And they partly overcome dimensionality curves because they don't construct the whole surface. They are just calculated when needed. And it turns out that when needed means less than the whole multidimensional surface. But accuracy is kind of in between, perhaps 1 kcal per mole, and they are extremely expensive to use. So here they can be used maybe instead for 1 million atoms, for 1,000 atoms, and instead of a millisecond for maybe a nanosecond. It's about 1 million times more expensive than use of the empirical potentials. Okay, so what is symmetry-adapted perturbation theory? So it's a method which calculates those interaction energies, which I defined on one of the previous slides. In contrast to some other methods, it calculates interaction energy directly. It's perturbation theory, which calculates interaction energy. It starts from isolated monomers, then at this shorter distance, when you bring monomers together, you calculate directly interaction energy, no subtractions. This name symmetry adaptation, you may think what it is. So it's some kind of technical issue. Electronic wave functions have to be antisymmetric, and in straightforward perturbation theory of this type, they are not. So we made them antisymmetric, which is equivalent to enforcing Pauli exclusion principle on the whole system. What is important is that SAPT decomposes interaction energy into well-known components such as electrostatic energy, induction energy, which in some fields is called polarization plus charge transfer energy, dispersion energy, and various exchange terms resulting from this symmetry adaptation. In fact, SAPT is the theory of intermolecular forces. If you go to any book on quantum mechanics, physical chemistry, whatever, and there is something about intermolecular forces, it's really a version of SAPT. You can calculate two-body interaction energy, three-body interaction energy. We have this in our programs. And in particular, I will be talking and showing results obtained with a version of SAPT, which is called SAPT DFT, where DFT is density functional theory still. So in this approach, monomers, like those, are described using Kohn-Sham DFT and time-dependent DFT, but interaction energies are computed using wave function theory. And I don't go into any details, but it's a fast method which works very well. So if you are interested in SAPT, you can go to our webpage. SAPT is available for free to everyone who wants it. We have recently published this paper in Journal of Chemical Physics, which is kind of SAPT code based. So we say, we give some kind of introduction and then tell what are possibilities of calculations using our codes. SAPT is quite accurate, and here is a new book published this year by David Micha, book on molecular interactions published by Wiley, and he gives quality of various methods starting from MBP2, this couple cluster singles, doubles, parenthesis T, kind of golden method of electronic structure calculations, but he put SAPT above. Well, that's nice for us. I would say SAPT is about as time-consuming and CCSD parenthesis T. What we can do? Yes?
The question in the chat.
How do I go there?
Okay, let me ask. Does interaction energy is affected by atmospheric pressure and temperature?
No, no. So well, the short answer and long answer. So what we solve here is Schrödinger equation, time-independent Schrödinger equation, which of course is at 0 temperature. So there's no pressure, there's no temperature at all. Now, this once you get a force field, you can use it in molecular dynamics calculations, and those are dependent on pressure and temperature. And in fact, I briefly mentioned that since we are in crystal structure predictions, we are one of the few groups which are actually using MD, and we get results dependent on temperature. So there's some work from our group which is relevant, for example, for atmospheric science, for people who are using our results, working on water vapor in Earth's atmosphere. So there are extensions to atmosphere as well, but not directly from quantum mechanics, but from molecular dynamic simulations done with those potentials.
Krzysztof, another question. How does the cost of SAPT compare to CSD parenthesis T and CSDT?
So I will talk about in a second, okay? So what we can do now, it's a calculation which runs just on a couple of cores for about 2 weeks. You can do it actually on a well-equipped laptop because we use only a couple of cores. So it's almost 400 atoms. It's half of complete DNA term. So this is a complete DNA, not only the DNA base, but everything else. And we can calculate interaction energy, which I think is first reliable result for system as large as this. Okay, so automatic development of those potential surfaces. So I already mentioned huge human effort, and I already mentioned that we use machine learning. Huge computational effort of single calculation, and here is the answer to this question. So I already said that accuracy of this SAPT-DFT is close to CCSD parenthesis T, but SAPT-DFT scales as n to the 5th with system size, and CCSD scales as n to the 7th. So in this paper, which I flashed for a second a few minutes ago, we compare with so-called linear pseudo-natural orbital method, which is fastest possible CCSD of T, which is available in ORCA, and SAPT is many, many times faster. So the other problem was that people use huge number of grid points, low accuracy of feeds, and got often long-range behavior. And all of this, I will not go into details, was fixed in these papers, and we have now positive answers, and we can develop potential for really large molecules. So now I'll go to the main subject, crystal structure predictions. So I already said it is difficult. In fact, in 1988, Maddox, who was editor of Nature, says that one of the continuing scandals in physical science is that it remains generally impossible to predict structure of even simplest crystalline solids from a knowledge of their chemical composition. And then there were several other papers later saying, no, no, you cannot do it. And so I already discussed why it is so important for pharmaceutical industries, and other places where it is important are energetic materials, nonlinear optical materials, photovoltaic cells, and many others. So it looks like really hopeless situation, but things changed since 2008 to 1998. So in order to check this progress, Cambridge Crystallographic Data Center started to do so-called blind test of CSP. The first was in 1999, and basically confirmed the answer no, nobody can predict crystal structure. The sixth test in 2005 was really coming out better, but still, so those were the monomers in this test. And for different monomers, the number of correct answers were like this percentage. But I also have to reveal that to be in the success range, you can provide 200 structures. The root mean square deviation can be as large as 0.8 angstroms, and hydrogens are not included. So it's not really, you would say, it's not so, the criteria are quite kind of lax. So how do you do crystal structure predictions? So you have to optimize monomer geometry. You build the whole crystal force fields from two-body potential interfaces. Then there are two important stages. One, you have to get some initial guess. It's called packing stage, when you just put molecules in a given symmetry, crystal symmetry group, and then there are various methods, but it really boils down to squeezing the crystal until van der Waals spheres touch. So you get about 500,000 candidate structures typically. And then you look at most dense polymorphs, because we know that most dense polymorphs are easiest to obtain, and you obtain of the order of 10,000, 50,000 most dense polymorphs. And then you minimize energy with some potential. You cannot use
You still respect the symmetry, space group symmetry when you do all this.
And in this minimization, you keep the space group symmetry. Okay. That's why it is possible. And then you perform MD simulations when you don't respect symmetry anymore, but it's kept actually for about 1,000 lowest energy structures, or you can perform periodic DFT optimization. And then you get crystal structures. So we had time to do in the sixth blind test only one molecule, the system 22. We were the only successful submission. There are many other groups who were trying to do first principle prediction, but we are the only one who got correct answer for this crystal. Our rank was 2 to 4, which is not bad. You can submit 200 crystals. So it was high in our ranking. And we had best RMSD of all submissions for all crystals. And it's published in this paper. We collaborated with a couple of groups. And we can now calculate force fields for very large molecules quickly. So this was done by 2 of my graduate students in about 2 months. It's a project, collaborative project, still unpublished results. So to explain what I want you to explain, I have to talk a little bit about the form of the force fields. So those crystal structure predictions program can use only very simple form fields in this minimization stage. This so-called X6 plus Q, or Buckingham potential, which has just exponential term, like some dispersion energy 1 over r to the 6, and electrostatic term. But this form is not flexible enough to fit this ab initio potential on the surface. So we have a more complicated form, which has some similar elements. This is similar to this. this first term is similar to this is similar to this, but it's more complicated. But those programs don't take it. So what we did recently, and we are hoping to publish it soon, is one technique. No, it's a simple idea, but it really changed this field of first principle predictions. So to understand what we did, let's repeat what I already said. Packing, sorry. So packing can use only primitive force fields, like Lennard-Jones. It gives you initially 500,000 polymorphs, and it packs it to say 30,000. Then you minimize them, but you can use only those simple force fields. And you take 1,000 polymorphs with lowest energy. This is like, think of having 500,000 people and you look for one guy. How do you find this one guy? So first thing is that you want to be sure that it is in this 500,000 people. So the first step, this packing, and must assure that the polymorph which you look for is here. And really, like 50 or more years of experimentation in this field have shown that packing which produces this number of crystals is good enough, that it never misses the crystal. And also the sorting by density, if you produce as many as 30,000 crystals, then you are sure it is there. So what you can do, then you can do MD with SAPT or periodic DFT on all those 30,000 crystals. But the problem is that if you do 30,000 such runs, CPU time is measured in years, and it will take you on single core, but still 50 years. So you cannot do it. So what is really done, what we have done in blind tests and other people are doing, you do the first step as above, but here you do first minimization, and you do this X6Q optimization, and you reduce 30,000 polymorphs to 1,000 polymorphs. Then you can do the same step 3, which is like the step 2 here, but on 1,000 polymorphs. And you get pretty reasonable answers. The problem is that this step very often loses the right polymorph. And it is still quite time consuming. So notice that years change to days. So this is this method 2. You do 1,000 runs, and you have to do like, with periodic DFT, you have to use about 700 days, which, if you do it on 700 cores, it's okay, you can do it in a short time. But what we recently implemented is a fairly small change, but very important change, that the 0K optimization is performed with full SAPT potential. So, and we, instead of producing 30,000 polymorphs, we produce only 10 polymorphs. And then we do the same step like here, but only on 10 polymorphs. And this is still in days, but instead of 800, the top is 80. So right now, potential energy development is the main cost, and all the rest is very negligible. And you always get, in this way, #1 polymorph. So those are our results. Various systems from those blind tests which we tried so far. And as you can see, we get very good rankings. There are a couple of cases where the ranking is not in top 10, but doing 30 such runs is still not a big problem. We have very good RMSD, well within blind test range, and we did it for a couple of molecules from other than blind tests, and we get everywhere very good ranking. And when you do, so this is rank after the 0K minimization. Then you do MD or periodic DFT, and in all cases you get rank 1. And this is how it looks. So like for this system 1, we have 0.9 angstrom RMSD. It looks like single molecule because the experimental crystal and theoretical crystal literally overlap. Here you can see small differences, and here as well, but in general, the representation is very good. So I see that I'm out of time. So I have here a slide about our extensions. I will just say that we can do larger SAPT calculations right now. I told you that I won't be able to talk about this fragmentation method that John is working on. This flex auto PS works very well. We published a paper recently. This is showing how well it works on a simple system, water dimer, where you have computed points as dots and fit our lines, so you can see excellent agreement. Here's a larger system where you have several soft degrees of freedom. And again, it compares well with, well, it's just empirical potential of PLS, but it was fitted on this system, so it's quite reliable. And in summary, we have a method which gives CCSD of T accuracy at the cost of empirical force fields. AutoPS uses machine learning and reduces the cost of development by order of magnitude. And we can now very reliably predict the crystal structure of about 20 atom monomers in 1 day of real time if you use 70 cores, which is not a problem at all. So we have not applied those systems. We have already SAPT code which can do it. We are going to do monomers with 50 atoms, which will give us basically, somebody says that 80 atoms is 80% of pharmaceutical drugs. So we can do about 80 atoms, and we can do 80% of molecules of interest to pharmaceutical industry. I knew I won't have time to talk about how you can, so we can develop surfaces for flexible monomers, how we can apply it in crystal structure predictions as another subject. And we also can construct monomers even larger than this from fragments. This wouldn't be really that much work for crystal structure predictions, but rather for biochemical applications when you can do proteins and things like this. Okay, that's all. Thank you very much.
Okay, thank you very much, Krzysztof. Okay, there are a few questions here. Then, of course, I have a few questions. And if anybody has other questions, you can ask. So let me ask these few questions first. So thank you very much again, Krzysztof. The first new question to ask is, in SAPT, what is the perturbation parameter?
So perturbation parameter is interaction between all particles of one molecule, I call it monomer A, and another molecule, monomer B. So in zeros order Hamiltonian is just Hamiltonian for monomer A and Hamiltonian for monomer B. So if you form from A and B complex AB, then in this complex, you have, of course, interactions of electrons of monomer A with electrons of monomer B, and nuclei of monomer A with electrons and nuclei of monomer B. So this is the interaction potential. To repeat it, interaction potential is sum of all Coulomb interaction between particles of monomer A and particles of monomer B.
Okay. But Krzysztof, I thought SAPT was the double perturbation theory, no?
Yeah, so I didn't go into those details. So if you have a small system, you can get solutions for monomers practically exactly. You can use full configuration interaction, and we publish several papers with such calculations where monomers are essentially exact. And then you can, there is just single perturbation theory. The only perturbation are those interactions of particles from different monomers. But in practice, for other molecules, you cannot do it, of course. So what you do, you solve those particles at, you solve, instead of Schrödinger equation for a given monomer, Hartree-Fock equation. Those can be solved quite accurately. So you have accurate Hartree-Fock solution, but you are missing correlation, correlation of electrons within each monomer. So then you do what Omololu said, you do double perturbation theory when you correct simultaneously for perturbative effects of both operators. So one operator is this intermolecular interaction operator, another is intramolecular correlation operator, which is sometimes called Meller-Plesset fluctuation potential. That's why in quantum chemistry they have this strange name, MP2 theory, MP3 theory, and so on. Okay. So that's kind of SAPT, which was developed very early on. In fact, my PhD thesis was the first publication where the double perturbation theory was really used, when those corrections for intramonomer correlation were included in interaction energy. But what we do in those crystal structure work is we use the SAPT-DFT. So SAPT-DFT actually assumes that the correlation inside monomers is taken care by DFT, okay, which is an approximation, but works quite well. So SAPT-DFT is single perturbation theory again.
Okay. The other question, thank you, Krzysztof. The other question is about auto-PS. How do you remove the holes in the potential? So instead, for instance, for water dimer, when you get two water molecules get close together, doesn't your potential just go to minus infinity? How do you remove the holes?
Yeah, so holes are kind of problem for everybody developing force fields, except for Lennard-Jones, because Lennard-Jones has repulsive term 1 over r to the 12, so this takes care of, they don't have holes. Okay. But everybody uses, even using Buckingham potential or any exponential potential have holes, because of course exponential goes to a constant when distance goes to 0, and 1 over r to any power goes to infinity. Yeah. So holes are kind of everybody's scarce. So what we do, we use several methods, kind of complex, multifaceted approach. So one way of removing holes is that we, after the potential is fitted, we check for the holes. How do you check for the holes? You go from infinity at a given configuration, and when the potential goes up on the barrier, you check how far it goes up. If there is a hole behind barrier at some point, it will have, it stops going down, going up and goes down. So we have a hole, and then you put additional point at the place of the hole, and then refit the potential. Because refit is automatic, it's not a big deal to do such a refit, and this basically makes the potential to be repulsive, because it knows at this point you have ab initio energy which is positive and large. So that's one way of removing holes. Another way of removing hole, which we introduced in this 2016 paper, which I cited, is that we actually added kind of like Lennard-Jones term. We added like this 1 over r to the 12 term. but this term is chosen with such parameters that has negligible effect at important region of potential in the surface, but at very short distances, it prevents deep holes because it prevails at very short distances always. And so one advantage of those potentials is that, you know, when you don't take care of the holes, the hole at short distance can be, for example, minus 100,000 kcal per mole. If your simulation gets there, you are dead. With those 1 over R12 terms, we have holes. They are still holes, but they are always on positive part of the potential. So even if the simulation gets there, it will probably get. So there's a local minimum at positive energy, but it's not as dangerous as minus 100,000 kcal per mole.
Okay, that's fine. Thanks. Krzysztof, let me ask you a couple of questions. How do you deal with metastable structures? So for instance, if suppose at some temperature, the crystal is metastable, how do you know this is metastable and not the global minimum?
Yeah, so of course, we don't know it, and nobody knows it. So we are never sure if we get global minimum, but when I compare it with those experimental structures, actually nature is very good in getting global minimum. So if we get experimental structure, then we are fine. In fact, you know, all the polymorphs except for one are local minima.
Okay.
They are always local minima because they are obtained in this minimization step. The step is well converged, so there's always a local minimum.
Okay.
And so it's really, you may say, it's a game of local minima. Find out which of the local minima is the global one.
Okay. So in your MD, you don't include quantum effects, hydrogen quantum effects?
No, not yet. Not yet. That's, I think, is really, it would be nice to have it, but it's far on the list of most important things to take care. In fact, as I already mentioned, our group is one of very few groups which does any MD, any temperature-dependent predictions for crystals. Most people just do 0K predictions. So okay. The next step would be quantum MD, and I have a student working on quantum MD, Omer knows him, Omer, who is supposed to do quantum calculations, but just for water, not for those big monomers.
Okay. A couple of more questions. So, Chandra, please could you ask your question? Just turn off, or mute your mic, and then you can ask the question. Chandra Mishra. If you can just unmute your mic and ask the question. Chandra Mishra, are you still there? Okay. So Krzysztof, another question. Oh yeah, please unmute your mic and ask the question. Oh, I should unmute you. Okay, let me try. So Krzysztof, can you tell us a little bit about your machine learning approach?
Okay, so this is a wonderful work done by Mike Metz. And
also tell us about, in general, your attitude towards machine learning for interaction energies.
General attitude? Yeah. So general attitude is that it's much over-advertised, and it works much worse than people usually say. So they give you good results and they don't show you bad results. So here is one well-known paper which develops a method which is called intermolecular potentials from machine learning and published 2 years ago. And so we use this method for the ethylene glycol, and it works pretty well at long range. It is expected to work pretty well for long range because it uses basically well-established method of multiple expansion, which we also use, so that's fine. But at shorter distances, these repulsive forces are much harder to predict, and as you can see, it gives here really worthless results. And we tried it for a couple of other molecules, and in most cases, I mean, in some cases it behaves well, of course, but in many cases it is really worthless. In fact, for the same systems, with a system as simple as phenol, which is benzene with OH group, for some configurations, it works perfectly well, follows SAPT very accurately. For other configurations, it gives like energies which are a couple of times too large at short distance.
Okay, thank you. So he will ask his question now. Kashlesh Chandra Mishra, please ask your question.
Hello.
Yeah.
Hello.
Yes?
Yes, I can hear you.
Yes, sir. So actually, I'm asking, when we try any of crystal prediction, then we use basically machines. So we use atoms of machine in the sense, if we use machine or CPU, then actually there are atoms which are working. So I am asking basically that why not we say that it is the combination effect of the crystal which is we analyzing and the machine which we using to analyze it.
Yes, sorry, I can hear you very, very poorly, and I just
actually I
couldn't hear you.
India, so signals maybe some have destructions. Hello?
Yeah, now it's better, so maybe you can repeat.
Yes. So I am asking, when we use any of crystalline method to predict the crystal structure, then we basically use the atoms of machine to analyze that crystal. So why we not say that the crystals of that machine and the material which we are analyzing, we see combined effect of both rather than individual ones?
Yeah, so of course this is obvious thing to do, and I don't know if anybody has done it for crystal structure prediction, but people do it for molecular dynamics. So basically, you do molecular dynamics using machine-learned potentials. And however, this is not this type. So this IPML is in a sense like using quantum mechanics. So you take arbitrary system and you predict potential and surface. This does not work at this point, as you can see on this graph. Yes. But so what people do, they use machine learning. So they would produce some large number of data points for a given system. Using quantum mechanics, like using DFT plus D, then use some neural networks to feed the specific system and use it in MD. And this works quite well. And it reduces costs by about 3 orders of magnitude compared to Karp-Marinello direct simulations, with fairly small reduction of increase of error.
Okay.
Yes. Okay.
Thank you, Krzysztof.
Thank you so much, sir.
So how is Flex Auto PS different? Don't you use machine learning also for fitting?
So it is in the intermonomer part, it is quite similar, except that all expansions include, so I don't have any slide to show this, but if you have this potential like this, and all those RAB A belongs to system monomer A, B belongs to monomer B. In addition, this is multiplied by some powers containing like A and A prime. So this is of between centers of a single monomer. And there are some parameters which are fitted. So we fit the complete non-rigid potential in this way.
Okay. Okay. So finally, maybe you should tell us something about two-body SAPT and three-body SAPT, the cost, and maybe a little about the procedure.
So two-body SAPT is, of course, the SAPT I was talking about, and this calculation, which I have shown for this half of DNA term was two-body calculation. So you cannot see it very well, but this is DNA helix. So there are two chains of DNA. Each chain is single monomer, and the other chain is another monomer. So in this way, we calculate interaction strengths between two components of the helix. So how strongly helix is bound. So this two-body SAPT can be applied to systems like this. Now, three-body SAPT, we have a method which we developed with Rafał Podeszwa in 2008, which is a fairly simple method, which, however, works quite well and can be applied to pretty large systems, not as large like this, but probably to systems with maybe 100 atoms. So this method is actually combines many-body perturbation theory at second level. So you do MP2 calculation for a trimer, which are pretty fast. But of course, MP2 does not include important three-body components such as three-body dispersion energy. So those of you who have heard about this famous Axelrod-Teller-Mutto interaction, it's not in MP2. And we add to it a term which is three-body SAPT term, which we called third-order dispersion energy, which is fairly easy to calculate. It's not very expensive, and can be calculated for basically as large system as MP2 can be calculated. And it gives pretty good results. In fact, one popular method is what people use. They use empirically fix this Axelrod-Mutto-Teller energy, ATM, so-called ATM energy. And our method works approximately as well at approximately the same cost, but is fully ab initio method, not some kind of empirically fitted method.
Okay. Thank you very much, Krzysztof. So we'll end here. Please, can you send your slides to us, like
sure,
PDF? Yeah.
Sure.
Thank you very much, Krzysztof.
Okay, thank you. Thank you to everybody. I appreciate your interest. Bye-bye.
Bye.
Thank you.